So for determining stability, we need to take an air parcel, as we've discussed, and compare it with the surrounding environment. So to do that, we need to know what the environment's like and take an air parcel and change it by the dry adiabatic or moist adiabatic lapse rate. And you can determine stability by basically air that is colder than its surroundings is more dense. Dense air sinks. Sinking air is generally stable air. Air that is warmer than its surroundings is less dense than the air surrounding it. Less dense air rises. Rising air is generally unstable air. So to get the surrounding air, we need to know the environmental lapse rate. That's the actual change in temperature as you go up in the air. And you get that by using a weather balloon. You attach a sensor package to it, send it up in the air, and it gives you the environmental lapse rate, which is an observation of how the temperature changes with height. So then you take that environmental lapse rate and you have a theoretical parcel. If you force the parcel to rise, it will rise at, if it's dry, at the dry adiabatic lapse rate, which is 10. So it would be always colder in this scenario than an environmental lapse rate of 4. Same thing for the moist adiabatic lapse rate. The moist adiabatic lapse rate is 6. Say you had a moist parcel and you take it, you attach it to a helicopter, force it to rise. It changes by 6. It is always colder than its surroundings. Meaning it always wants to sink back down to the surface. So this is an absolutely stable scenario because it is colder than it moved at the dry adiabatic lapse rate. It is colder than the environment, and moved at the moist adiabatic lapse rate. It is colder than the environment. So in both cases, it is colder than the environment. So you can think about the ways you could get stable air. Basically, low differences in temperature between the surface and air aloft. If they're very similar, you're going to have stable air. Or just any area where there's not a big change in temperature. Warm air being advected at the top of the atmosphere would cause more stable air. Surface cooling would cause stable air, and that happens through radiational cooling or cold air being advected along the surface. Now, moving on to unstable air. Unstable air, as discussed, will move away from its original position when forced, and it comes in 2 forms: absolutely unstable and conditionally unstable. Starting with absolute instability, again, we look at comparing it with a dry environment, or a dry parcel, and a moist parcel. So you have an environmental lapse rate of 11. If you take a parcel and force it, it's dry, it moves at the dry adiabatic lapse rate. Again, it goes up, it's 20. It is warmer than the environment, 19. Wants to move up another kilometer, it's 10 now, because it's moving at the dry adiabatic lapse rate of 10. It's warmer than 8. The parcel is always warmer in this scenario, so in the dry case, it's unstable. And then you compare with the moist rate as well, and again, 6 versus 11, move it up. It moves at the moist adiabatic lapse rate, so instead of being 30, it cools to 24. The environment is 19. It's warmer than its surroundings, so it keeps wanting to move up. So when the environmental lapse rate is higher, so it cools more than both the dry adiabatic lapse rate and the moist adiabatic lapse rate, you get an absolutely unstable environment. This rarely occurs, except for in very small areas, because it takes extreme changes in temperature over an area. The more common form of instability is conditional instability, and that's where it is for a dry parcel, stable, and for a moist parcel, unstable. So consider an environmental lapse rate of 7 degrees Celsius per kilometer. It is colder when forced to rise than the dry, when forced to rise at a dry rate of 10, it's colder than the environment. So again, starting at 30 degrees Celsius, it rises a kilometer. The environment is 23. The parcel, cooled at the dry adiabatic lapse rate, is 20. That's colder. It wants to sink. A dry parcel is stable. Now comparing with a moist adiabatic lapse rate, again, starting at 30, the environment, raised a kilometer up, is 23 degrees Celsius, but a parcel forced at the moist adiabatic lapse rate is 24. That's warmer. It wants to rise. It is unstable. So from a moist perspective, it is unstable. From a dry perspective, it is stable, and that's why it's conditionally unstable, because it depends on the state of the parcel. So causes of these unstable layers of the atmosphere: basically air aloft becoming cold, cold air advection aloft, clouds emitting infrared radiation to space. This causes instability. You can also have surface warming. This is a big part of why surface warming can cause thunderstorms. Daytime solar heating, warm air advection, basically all this warms up a low level of the atmosphere, building up energy, making air want to rise. And all of this can be summed up in this one chart. Basically, you have the dry adiabatic lapse rate in red, the moist adiabatic lapse rate in blue, and different area where the environmental lapse rate falls tells you whether the environment is stable or unstable, or a parcel would be stable or unstable. If the environmental lapse rate falls in this area, it is absolutely stable. If it falls in this area, it is absolutely unstable. If it falls between the two lines, it is conditionally unstable.